Okay, happy Sunday afternoon, tinkering radio fans. Let's look at designing with RF chokes, especially these little handy-dandy little common mode units. Got the lights turned down so that we can look at the oscilloscope display. A choke is intended to be an open circuit to RF. An inductor is a different thing. Inductors have some kind of intentional calibrated reactance. A choke is supposed to be an open circuit. On the left is just a single choke on an iron or ferrite core. See the two solid lines? That indicates the type of core. With a common mode with two windings, there can be 4 configurations. Use a single winding. Use both windings in parallel. Then there are 2 series combinations. See the dots? The one on the left is series aiding, which means when the current goes through both windings, the magnetic fields are the same direction and they add. Then there's series opposing. And series opposing is with the polarity or phasing dots the opposite. Magnetic field cancels. The beauty of these commercially wound chokes is that they're wound very precisely, and especially in series opposing, there's an extreme cancellation of the magnetic field. So when you put the common mode choke on an inductance meter, it reads 0. So here's a high current common mode choke I'm testing. I'd intended to use these in the filament supply of my 600 watt 4-400 amplifier driven by about a 30 to 40 watt exciter. And question is, what's its pass band or suppression band? How does it act with wideband RF? And will it overheat? Will it burn up? So here is the choke. Connected with a 50 ohm resistor. Right there. Let me put the oscilloscope across the resistor to indicate the current. And we turn on the generator at a blazing frequency of, we can't read because there's too much light in the background. At 1 kilohertz, we get a scope display of 1, 2, 3, 4, 5 divisions at half a volt per division, which is 2.5 volts, which agrees with the reading on the generator. So the choke is basically short, and it's just reading across the resistor. When we go to a sweep from 1 megahertz to 60 megahertz, we see tremendous RF suppression. We see a little hump right there at about 21 megahertz. There's another bit of a hump out here close to 60 megahertz. But now the amplitude of that signal on 500 millivolt per division is only about 200 millivolts out of 2.5 volts. And you can get a decibel volt calculator online and calculate the suppression in dB, going from 2.5 volts down to about 0.2 volts. It's quite a bit. But we don't see any particular peaks or valleys in that response. Way down here is 1 megahertz on the left. We can't see anything in particular at the low frequency, so I'll run it down to, I'll start running to see the peak starting to come up there on the far left. Right over here. As the frequency goes down, that choke starts becoming of less reactance. So how do we predict what's going to happen with this in the circuit? Well, the circuit it's going to be in is an RF generator, which is the RF transmitter exciter at 40 watts. Draw a little schematic here. That'll be the circuit. A 40 watt AC RF source through that choke, and the power supply is going to be a 22 amp 5 volt switch mode supply at about what's 5 volts divided by 16 amp is, the supply represents about 0.3 of an ohm. There'll be a lot of capacitance across it, so it's basically a dead short. So what that's going to do is put that choke across the 40 watt exciter supply, and it is going to come unglued. It will turn into volumes of smoke within about 5 seconds, except that the exciter, being a solid state rig, will see a short and it'll turn the power down. But if this were a tube exciter, it will absolutely incinerate that toroid core. How do I know that? From this. Because this is a Born's 8115 RC common mode. It's for suppression, which implies it's a suppression core, and suppression means that the core eats the energy. We'll turn it to heat. 40 watts worth will turn it into charcoal, and the smoke will chase you out of the room. Now, the way we know that by looking at this trace is that it's not a conservative core, it's not an inductance, because if it was just an inductive reactance, the attenuation would go up with frequency more or less linearly, and then there would be some anomalies in the frequency response. When I tested one of the smaller high voltage cores in series opposing, there was a lack of attenuation getting down about 100 kilohertz. The attenuation at 4 megahertz was reasonable, and the attenuation was extreme at 12 megahertz, and then started going back up. That indicates a resonance, or resonances somewhere, but predominantly suppressive, because the resonances didn't result in very high peaks. But this flat response indicates it's a suppression core that's eating the RF. And when it suppresses, that means dissipation in the core. That means turning it into heat. So this is only suitable for low levels of RF. So that core has to go. It's a fine core, created extremely good broadband attenuation up to 60 megahertz, probably more. But in this application, it's worse than worthless. It will incinerate itself. Now, this little high voltage common mode that I tested has a response like this, down to a pinch off. And it goes something like that. And the max attenuation is here at 12 megahertz. And there's 4 megahertz. And there's a peak up in frequency, 20 or 37 megahertz. So not a bad pass band. The attenuation, that choke will work on the high voltage tube supply, because before that supply is a large capacitance, which is these doorknobs. That's 3,000 picofarad worth of 5 kV doorknob capacitors. And that's what the RF current is drawn from the plate. So that point is not particularly high amplitude of RF. But if it should become that way with a 600 watt amplifier, it will also turn that core into ashes. So what I'm going to have to do is abandon both these cores, because they're almost certainly suppressor material. And I just bought a pile of new ferrite non-suppression cores. inductive course for HF, and I'll have to wind chokes, inductive chokes, not suppression chokes, for these power applications for HF. Now, how do we know how to determine whether there'll be excess dissipation? Well, I did a video a couple weeks ago on testing RF components at power, where I showed you a dummy load with, say, a wound inductor. And so you can get an idea of how to do that from that video. So this is how we use principles of these cores and core materials to know whether the thing is suitable for this application or not, and they are not. So sometimes the answer is no, we have to do something else. So there's a really good example of application of chokes by K8byp